I'm going to go through titrations with you. Titrations and the calculations related to them are something that students find tricky, both at GCSE and at A-level. So, chemical titration, I'll work through one and we'll go through the calculation at the same time. In this first titration, I'm going to use an unknown solution of sodium hydroxide, unknown concentration sodium hydroxide, and I'm going to use a known concentration of hydrochloric acid. So I will use this to identify the concentration of this one. My known hydrochloric acid I need to put into the burette. So use a funnel and pour in. Throughout the titration, always think about this conversion factor of 1000 between moles per decimeter cubed and moles in each centimeter cubed. I've slightly overfilled the burette, and what I want to do now is run some of the hydrochloric acid through the burette until we get down to 0.
Into a conical flask I will put 25 centimeters cubed of my unknown sodium hydroxide. I use a volumetric pipette to get a precise measurement.
So 25 centimeters cubed of unknown concentration sodium hydroxide in here, 50 centimeters cubed in my burette of the hydrochloric acid of a known concentration. So I need to add the hydrochloric acid to the sodium hydroxide until it's neutral. To let me know when it's neutral, I'm going to use an indicator. In this example, I'm going to use phenolphthalein indicator. Just a couple of drops of that. Now, phenolphthalein indicator changes colour at the end point. It will go from pink to colourless. So I now need to add my solution. Now, what I'm going to do is I'm going to watch here. I'm not going to look at the amount I'm adding. I'll measure that afterwards. I know we're starting at exactly 0, so I'll be looking down here and following the titration a bit more closely.
In this reaction, 1 mole of hydrochloric acid neutralizes 1 mole of sodium hydroxide. So if I know how many moles of hydrochloric acid I've added, that is the same as the number of moles of sodium hydroxide in the flask. Here, phenolphthalein has gone colourless, so I have reached neutralization.
So the hydrochloric acid that we had here has 0.1 moles per litre, 0.0001 moles in every centimetre cubed. The titer here was 36.15 centimetres cubed, so 36.15 lots of 0.0001 moles. I need to repeat that. I've got quite a nice value on there, but I need to repeat it because there may have been something in the flask, there may have been some unusual event that I didn't pick up, some contamination or other, and we would normally say you want to get 3 concordant readings. What we mean by that is 3 readings that are very close to each other. If I did it 3 times and one value was a bit away, usually the first one is the least accurate. We call that your test run. But if I did 3 readings and they were all the same, I can keep the first run. I'm happy with that. If I do 3 readings and 2 of them are very different from the other one, I would do another one, get 3 concordant readings. That will improve my reliability. The accuracy comes from the fact that I'm using a burette and I can measure with high level of precision. The resolution of this burette is 0.05 centimetres cubed. What we'd say is that if you have a graduation mark, you should be able to read halfway between 2 graduation marks. So I can measure, I have graduation marks every 0.1 centimetre cubed, so I should be able to read to every 0.05. So I could get a reading of 36.15, 36.2, 36.25 and so on.
So here's my set of results. I've got 3 very similar readings showing good reliability on the titration. The average titer here is 36.15, so I know that there are 0.0001 moles of hydrochloric acid in each centimetre cubed. So 36.15 times 0.0001 moles per centimetre cubed is 0.003615 moles added to the flask. Because the reaction has 1 mole of hydrochloric acid neutralizing 1 mole of sodium hydroxide, if I had 0.003615 moles of hydrochloric acid, it will have neutralized 0.003615 moles of sodium hydroxide. So that is how much sodium hydroxide was in the flask. If there was that much in the flask, and the flask contained 25 centimeters cubed, then I simply divide by 25 to get how much was in each centimeter cubed. And here's my answer. 0.001446 moles per centimeter cubed. And then I can just use my 1000 factor to convert that back to standard concentration units of moles per decimeter cubed. And the answer is 0.1446 moles per decimeter cubed. That's the concentration of sodium hydroxide in the unknown sample.